Welcome to Unit 1.8, Acids, Bases and Salts. This set of videos is going to take you through this entire topic. You'll need your workbook in front of you, your booklet of notes, and you need to work through the videos, filling in your notes where appropriate. And this first video will look at indicators and what actually are acids, bases, and the reaction of neutralization. On page 1 and 2 you have your specification, the points that you need to cover in this topic. That is continued on page 3, followed by a list of definitions that you need to be familiar with for this topic. So we'll start the topic off by looking at indicators. And the reason we need indicators is because acids and alkalis are often colourless solutions, so they can just look like water. And indicators tell acids and alkalis apart. By definition, they're a dye that change colours in acids and alkalis. So the first indicator that you need to be familiar with is litmus paper. And hopefully you remember from year 8 that litmus paper comes in two forms, red litmus paper and blue litmus paper. The thing to remember with litmus is that it's always red in acids and always blue in alkali solutions. And then you can see from your table of results here that the colour it is in neutral depends on what colour it starts. So if it's red litmus paper, it'll stay red. If it's blue litmus paper, it will stay blue. So litmus paper does not change colour in neutral solutions, and that's one of its limitations. So if I was just to use red litmus paper and the colour was red, I wouldn't actually know whether it was an acid or a neutral solution. Similarly with blue litmus paper, if I used blue litmus paper alone and it came back blue, I wouldn't know whether it's neutral or alkali. So I actually need to use a combination of both of these to tell whether it's acid, alkali or neutral. A further limitation, which is at the bottom of your page there, is that it doesn't tell us the strength of the acid or alkali. So say for example I work out that it's an acid, I can't tell whether it's a strong acid or a weak acid. It doesn't give us a variety of colours to tell us the strength. Next video is going to show us litmus paper being used. So the first indicator you need to be familiar with is litmus. And litmus paper comes in two forms, the red litmus paper and blue litmus paper. The thing to remember is that litmus paper is always red in acid, always blue in alkali, and then in neutral solutions it stays whatever colour it started. So let's look at an example of an acid. You can see we've got hydrochloric acid here. So let's test it in our red litmus paper. Remember our rule, it's always red in acid, so let's see if that works out. So you can see my red litmus paper hasn't changed colour, so the final colour is red. And then if I pop it on the blue litmus paper as well, you can see that the blue litmus paper turns red as well. So acid solutions always change litmus paper to red. Now let's try water. Water is a neutral solution. Okay, we'll test it on the red litmus paper. Hasn't changed colour, it's still red. And on the blue litmus paper, again, hasn't changed colour, it's blue. So with neutral solutions, they are red in red litmus paper and blue in blue litmus paper. In other words, the litmus paper doesn't change colour in neutral solutions. And then finally, we've got our alkali solution, sodium hydroxide, which is an example of an alkali. If we test it with the red litmus paper, we can see that it's blue. And in the blue litmus paper, we can see it also stays blue. So the rule with alkalis is that alkalis are always blue in litmus paper. If you turn over to page 5 now, we'll have a look at universal indicator paper. Now, if you remember, one of the limitations of litmus paper was that it doesn't tell us the strength of an acid or an alkali. And that's where universal indicator can come in, because it gives a range of colours depending on the strength of the acid or the alkali. And you can see here your pH scale, which again you would have met back in first year. And you can see that it gives a range of colours in different strengths of acids and alkalis, and that corresponds to a number, and that is what we call a pH number. and the video will show us universal indicator being used.
So one of the disadvantages of litmus is that it doesn't tell us the strength of acids or alkalis, and that's a benefit of universal indicator. So you can see the scale here, our pH scale. It gives us a range of colours which tells us whether or not a solution is acid or alkali or neutral, but also tells us the strength of the acid or alkali. And you need to know the two-step method. It seems very simple, but what we need to remember to do is compare to the colour chart. So let's use the example of a strong acid first of all, and you need to be familiar with your colours of the pH scale. So you should already know what colour you're expecting this to be. So what we are doing is we're putting a drop on the end of a glass rod, applying that to the piece of universal indicator paper, but that's not the method finished. We need to then go on and say that we compare it to the colour chart, because right now I can see it's red, but I don't know what that tells me yet. So I need to compare it to my colour chart. So I work along the chart until it matches up with one of the pHs, and you can see it matches up with the colour of pH 1. So I can tell this solution has a pH of 1, and we can describe it as a strong acid. So you need to remember that second point of compare to the colour chart. Often people forget that and lose a mark. So let's do a couple of other examples. Now we've got a weak acid. For example, vinegar would be a weak acid. We're applying 1 drop to the piece of universal indicator paper. You can see that it's turned orange, but then again I need to compare it to my colour chart. So moving across, I can see it's probably about pH 3. We'll try water next. Water we would expect to be neutral, a pH of 7. So apply a drop to the piece of universal indicator paper. We can see it's turned kind of a greeny, yellowy greeny colour. And if we take it, compare it to our colour chart, we can see it's probably somewhere between 6 and 7, which would indicate that our water is slightly acidic, but water should be around pH 7. But again, that idea of comparing to the colour chart. If we move to weak alkali, you can see we're starting to form kind of rainbow colour. Weak alkali, apply a drop, and again we need to compare it to the colour chart. The greens are all quite similar as they move from green to blue-green, but you can see there it's sort of between pH 7 and 8, so it's a very weak alkali. And then finally our strong alkali. Again, apply a drop to the piece of universal indicator paper and then compare it to our colour chart. We can see that it's about pH 12, but maybe between 12 and 13. So we can see that it is a strong alkali.
So looking back at page 5 now of your notes, we need to fill in the description of our different pHs. So if we have a pH of 0 to 2, that we describe as a strong acid. A strong acid. And if you want to label your pH scale up here, you don't have an awful lot of room, but you could put a bracket around your 0 to 2 and indicate that that is a strong acid. You could even abbreviate to SA. Might be helpful beside your pH to also write a colour, because your copy is not in colour in your notes. So 0 to 2 would be a red colour. We saw that in the video. 3 to 6 then, and you can see as the pH number gets bigger, our acid actually gets weaker, and that seems a little bit strange, but the closer we get to neutral, the weaker the acid is. So essentially, if you think of neutral as the midpoint, the more left you go of neutral, so the lower the number from 7 is the stronger acid, just as the arrows represent. And so 3 to 6 we describe as a weak acid. 3 to 6 is a weak acid. And the colours of that would be your sort of yellow-orange colours. So orange through to your yellow. Okay, 7 is the midpoint, which is neutral. So 7 we describe as neutral. Be careful of your spelling. Neutral, and that comes up as green. Okay, and that's marked for you there. Once we go right of 7, i.e. a number bigger than 7, the bigger the number is, the more strong the alkali is. So from 8 to 11, we describe as a weak alkali. And if you struggle to forget where your intervals are, so where it switches from strong to weak, if you have a look, there's 4 numbers that are weak acids and 4 numbers that are weak alkalis. There are 3 numbers which are strong acids, and we'll see that there's 3 numbers that are strong alkalis. So 8 to 11 are weak alkalis, so we'll write that in here. And that corresponds to a sort of blue-green colour. Blue or blue-green colour on the pH scale. And then finally 12 to 14, we can label our pH scale. There's 3 numbers there. That's our strong alkali. We'll fill that in our table here. The description is strong alkali. And the colour of a strong alkali would be your darker blues or your purple. You can see in the final column you've got an example of each category. So your strong acids, you've got like the acids that you would meet in the lab, hydrochloric, sulfuric and nitric acid. An example of a weak acid would be ethanoic acid, which is what is in vinegar, carbonic acid, which is what is in your fizzy drinks. Water is an example of neutral. A weak alkali would be ammonia. And then your strong alkalis, again, your the alkalis that you would use in the lab, such as sodium hydroxide and potassium hydroxide. So for a universal indicator, you need to know the pH numbers, what they correspond to. So if I give you a pH number of 4, you should be able to tell me that that's a weak acid. And you should also be able to tell me what colour it would turn universal indicator. And then your 2-step method, which is at the top of page 5, for how we actually use universal indicator to tell us the strength of an acid or an alkali. We can actually go one step better than universal indicator paper, and that is the pH meter. So if you were asked in your exam what is the most accurate way of measuring the strength of an acid or an alkali, you would say that it's the pH meter. And at this point we'll stress that pH is a small p and a capital H. And the advantage of a pH meter is that it gives the pH to at least 1 decimal place. Most of them actually give it to 2 decimal places. So rather than you comparing to the chart and getting a rough pH of maybe 3 or 4, you could find that it's exactly, for example, 3.45. Or if it's just a 1 decimal place, something like 3.5. So it gives a more accurate value of the pH. And so we can better describe it as a weak acid or a weak alkali and so on. So as we've looked at with universal indicator, and again with the pH meter, we know that different acids and alkalis have different strengths. And the proper term for describing a strength of an acid or an alkali is the word concentration. So we describe a concentrated acid as a strong acid. So you can see that here. A concentrated acid is strong. The opposite of that is a dilute acid, which is weak. And as with anything, if concentration is a measurement, we need a unit for that. And there might be units you're unfamiliar with, but concentration is measured in moles per decimeter cubed. You need to be familiar with that. And how we represent that is moles, which is MOL, per decimeter cubed. That means we need a /. Decimeter is DM, just like centimeters would be cm. And it's decimeters cubed. So it's going to be a little 3 up there. So those are units of concentration. You need to be familiar with those. And it gives us a representation of how strong an acid or an alkali is. So if we just look at acids here, if we have a solution of a concentration of 1 mole per decimeter cubed, if a solution was twice as strong, its concentration would simply be 2 moles per decimeter cubed. So I can tell that this solution is twice as strong as my original solution. But comparing it to 1 mole per decimeter cubed, if it was half as strong, literally we half the concentration, 0.5 moles per decimeter cubed. So we can use concentration to give us an exact idea of the strength of various acids and alkalis. We're now going to have a quick look at what acids and alkalis actually are. And what you need to know for each of them is the particle that they produce when they dissolve in water. So you can see with acids here, they all dissolve in water to produce hydrogen ions. And hydrogen, when it forms an ion, if you think of the hydrogen atom, it only has 1 electron because it has an atomic number of 1. And when it forms an ion, it will lose that electron to get a full outer shell. By a full outer shell, it's essentially an empty outer shell, which kind of seems the opposite, but it is content in that it doesn't have a partially filled shell anymore. It's lost 1 electron, so its charge is plus, 1 plus. And we can see that in the formula of our hydrogen ions. Now, I'm just going to make this a little bit bigger, so it's H plus, and then there is a state symbol afterwards that's AQ. Now we meant state symbols with ionic equations. AQ means aqueous. It stands for aqueous, which is another way of saying dissolved in water. And that makes sense to put that state symbol because we're talking about acids dissolving in water. When they dissolve in water, they dissociate to give us hydrogen ions. They break apart to give us hydrogen ions. So we're going to look at a couple of formulas of some common acids, and you actually need to know these formulas. So first of all, we've got hydrochloric acid, which has the formula of HCl. So let's have a look at what happens when hydrochloric acid dissolves in water. So I'm going to do my hydrogen in a different colour to make it stand out. So it's HCl, hydrogen and chlorine, and it dissolves in water, and we know that it produces H plus ions, hydrogen ions, because it is an acid. So it produces H plus ions first of all, and it's dissolved in water, so we put the state symbol AQ. And then I need to think, what is my other ion going to be? Well, you can see in my formula I've got Cl, so it's going to be a chloride ion. A couple of ways you can work out the charge. Firstly, because there is a 1 plus charge of my hydrogen, that means the chlorine needs to be -1 to balance that out. The other way you can look at it is by looking at the top of your group number with chlorine, and you should have written at the top of that group 7, that they all form a charge of -1 when they have an ion, when they're forming their ion. So our chloride ion is Cl-. And again, it's dissolved in water, and so we give it the state symbol AQ. So actually in hydrochloric acid, if I zoom in so I can make this a bit bigger, if we had a beaker of hydrochloric acid, rather than HCl molecules, we have H plus ions. And we have our chloride ions. So when dissolved in water, hydrochloric acid breaks into H plus ions, and then the chloride ion is your negative ion. Let's look at sulfuric acid. Again, you need to know the formula of sulfuric acid. You should learn it, is H2SO4. So let's have a look at sulfuric acid then. It's H2SO4. And we know by definition that all acids dissolve in water to form H+ ions. So I'm going to write that on the right hand side, H+ ions. But it's dissolved in water, so I give it the state symbol AQ. But have a look at the left hand side. I have 2 hydrogens within my sulfuric acid. So therefore, to balance this, I need to put a 2 in front of my H+ ions. I do not put a little 2 here. The hydrogen is no longer, it's not diatomic when it's dissolved in water. We don't put the 2 there, we just put the 2 in front as if we were balancing the equation. So you can see for sulfuric acid, every molecule of sulfuric acid has 2 hydrogens, therefore it's going to form 2 H+ ions. Then if we think what we're left with SO4. And what we'll come to learn is that sulfuric acid forms sulfate salts. And you should be familiar with that formula anyway. You should recognise it as SO4 is what we're left with. It's dissolved in water, so it's AQ. And again, there's a couple of ways of doing this. First of all, you could think that this is a sulfate ion. Check the back of your periodic table and you can see that sulfate ions have a charge of 2-. Or we can see that we have 2 hydrogen ions, each with a charge of 1+. So that's really 2 times +1, which is a total charge of +2 from my hydrogen ions. So therefore, my sulfate must have a charge of 2- to balance that out. Okay, moving on to nitric acid then. Again, its formula is HNO3, and you need to be familiar with that. Why don't you have a go yourself, pause the video and see if you can write the equation for nitric acid dissolving in water, just as we've done with hydrochloric and sulfuric acid. So pause the video, give it a go, and then you can replay to check that you've got it right. So if we look at the formula of nitric acid, it's HNO3. We know that all acids dissolve in water to give us H+ ions. And we only have 1 hydrogen, so I only need 1 hydrogen ion. What I'm left with is NO3. And if we think about what charge it's going to have, the charge of the hydrogen ion is plus. Therefore, the charge of the nitrate ion, this is going to be minus. Again, it's dissolved in water. This is what we call the nitrate ion. And we will learn that all nitric acid reactions always form nitrate salts. And we get that nitrate salt from this reaction where nitric acid dissolves in water. So this is what we call the ionization of acids, or the dissociation of acids, as it's described there below. And it always becomes the H+ ions, and the other one is an anion, because we need a negative charge to balance out the positive charge from our hydrogen ions. So earlier on we were talking about strong and weak acids. So strong, we use the term concentrated, those two things mean the same thing. Weak, we use the term dilute. And what makes an acid strong or weak is how much it ionizes in water to form these ions, to form these H+ ions and the anion, the corresponding anion. And basically, the more H+ ions you have dissolved in water, the stronger your acid is going to be. So we describe a strong acid as one that completely ionizes in water. So all of the acid molecules are going to break down into your hydrogen ions, which cause your acid to be strong, and your anions. Whereas a weak acid only partially ionizes in water. That means some of the acid molecules break down into the H+ ions and the anions, and then others don't. And what we see is that the more ions, more hydrogen ions that you have dissolved in water in the end, so basically the more acid molecules that break down to produce these H+ ions, the stronger the acid will be. And if we think back to our pH scale, remember 7 is neutral in the middle, and then going left was increasingly acidic down to 0. So the lower the number, the stronger the acid. So if we've got the more H plus ions dissolved in water, the stronger the acid is, and therefore the lower the pH is. Sometimes we think it's going to be the higher the pH because that'll give a stronger acid, but you need to remember that the low numbers, 0, is your strongest acid. Okay, and you've got a summary down at the bottom there that concentrated acids will have a high number of H plus ions present in solution, causing it to be a strong acid, and dilute acids have a lower number of H plus ions because their acid molecules have only partially dissociated or partially ionized in water. It's a very similar story with alkalis, except what defines an alkali is that it doesn't dissolve in water to produce a hydrogen ion, but it dissolves in water to produce a hydroxide ion. Hydroxide is OH with a charge of minus, and that appears in the back of your periodic table. Again, we've got the symbol AQ, which means aqueous, which means dissolved in water. So if I have a look at sodium hydroxide first of all, and we could get the formula of sodium hydroxide by doing swap and drop. So if you change your symbols into formula first of all, so we'll do Na for sodium, and hydroxide, you can see from my formula here, is OH. Don't worry about the charge for now, that comes into play later on. We now need to work out our valencies. So sodium is in group 1, so it has a valency of 1. And hydroxide has a charge of minus, so therefore it also has a valency of 1. When we swap and drop them, then we'll end up ignoring our 1s. So our formula of sodium hydroxide is NaOH. So when sodium hydroxide dissolves in water, because it's an alkali, we know it's going to produce hydroxide ions. I'm going to write that on the right hand side, because normally we write our negative ion on the right, the very right hand side of the equation. We write it second. It's hydroxide ions, and it's dissolved in water. And you can see from my formula that I only have one hydroxide ion. What's the other ion going to be? Well, it's going to be sodium. And again, a couple of ways you can work this out. Firstly, because I have a minus charge from my hydroxide ion, it must be a plus charge from my sodium. Second way you can look at that is look to the top of group 1 where sodium is, and you can see that all group 1 elements form a charge of 1+. It's also dissolved in the water, so we give it the AQ symbol. So what we're saying is that for alkalis, for sodium hydroxide in particular, if I had a beaker of it, in that beaker I would have sodium ions, we'll only draw a couple here, and I would have hydroxide ions. It wouldn't be swimming around as sodium hydroxide molecules, you'd have those individual ions present. Why don't you give it a go for potassium hydroxide? Potassium is also in group 1, so you end up with the same formula, just with potassium replacing sodium. So it's KOH. Pause the video, see if you can write the equation for the ionization of this alkali. So let's have a look at what you got there. Hopefully you can see that it forms a hydroxide ion because it's an alkali. It's dissolved in water, so I need my AQ state symbol. And then also the other ion that forms is a potassium ion, K+, again dissolved in water, AQ. So you can see that's a very, very similar equation. So again, this is the ionization of our alkalis. Ionization, the word makes sense. I'm forming ions. Remember, ions are charged particles. So I'm forming ions from my alkalis. And we always, they always dissolve in water to produce a metal ion, for example, potassium, and your hydroxide ion, which is what makes it an alkali. And again, just like with our acids, we said that acids, strong acids, completely ionized in water to give us hydrogen ions. It's a similar story with alkalis. So strong or concentrated alkalis completely ionize in water, so all of the alkali molecules break down to give you hydroxide ions and the corresponding metal ion. Whereas weak alkali only weak or dilute alkali only partially ionizes in water. So some of your alkali molecules will break down to give you your hydroxide ions and your positive metal ions. Others don't break down and just stay as the alkali molecule, and if they haven't broken down into their hydroxide ions, then they're not reacting as an alkali. We need those hydroxide ions to be free in the solution, essentially. And again, the same story with acid. As with acids, the more hydroxide ions we have dissolved in water, the stronger the alkali is going to be. And have a think how that's going to affect the pH. Well, if we take 7 as our neutral, the alkali region is anything above 7, but it goes increasingly alkaline as we get bigger, as we go further down the scale to 14. So actually in this case, the stronger the alkali is, the higher the pH is going to be. And just as we said with acids, concentrated alkalis are going to have a high number of hydroxide ions in solution. Dilute alkalis are going to have a lower number of hydroxide ions in solution, because not all of the molecules have broken down into the hydroxide ions and the corresponding metal ion. So now that we've had a look at what acids and alkalis are, we're going to have a quick look at the reaction of neutralization. So you'll be familiar with this reaction again from junior school, but neutralization is when we add an acid to an alkali and we get a neutral solution. So if we look at our pH scale here, you can turn back to the page where your pH scale is on. If we think about it, what we're doing is we're taking an acid, say of a pH of 1, we're reacting it with an alkali, say of pH 13, and what's happening is they're neutralizing each other, and in the end we get a neutral solution of pH 7. We have to add a specific amount of acid to a specific amount of alkali, and it depends on the strength of your acid and your alkali. So if you are trying to neutralize a strong acid with a weak alkali, say for example pH 9, you're going to need a lot more of the alkali because it's weaker to produce a neutral solution. And you need to know the exact definition of neutralization. So it's the reaction of a base, and we'll talk about the difference between a base and an alkali in a second, with an acid to form a salt and water only. So you've got a general equation there on your page. Acid plus alkali or base gives you a salt plus water. And the name of the salt, it's not just salt, it depends on the acid we use and the alkali that we use, but we'll come back to that later on. So what's actually happening in neutralization? And this is so important. The equation we're just about to write, if it comes up on your exam, it's worth 3 marks. It's really easy 3 marks to get if you know your equation, so please make sure you learn it. So we said just a minute ago that all acids dissolve in water to give us hydrogen ions, H plus ions. They're dissolved in water, so we give them the state symbol AQ. We said that all alkalis dissolve in water to give us hydroxide ions, OH minus, again with the state symbol of AQ. So in neutralization, we're reacting an acid with an alkali. And have a look at your formulas there. You've got an H plus and you've got an OH minus. How many hydrogens do we have in total? We have 2. So we can write H2. How many oxygens? We have 1. H2O, what is that? It's our water. And for the state symbol of water, we give it the state symbol liquid, because water is a liquid at room temperature. So the marks for this, you would get 1 mark for the left hand side, 1 mark for the right hand side, and 1 mark for your state symbols. Okay, so put a big star in it, learn this. It's worth 3 marks if it comes up. And this is what we call the ionic equation for neutralization, because you can see we've got the ions that are involved in the neutralization. And what it's actually saying is that it doesn't really matter what the metal of your alkali is or the anion of your acid is, but what we see happening is a reaction of our H plus ions from our acid, and you might want to write that underneath if you can squeeze it in. H plus ions from your acid, and your OH minus ions from your alkali. And if we think to the general reaction of neutralization, it's acid plus alkali gives us salt plus water. And so the H plus ions from your acid are reacting with the hydroxide ions from your alkali and producing water. So make sure you learn that equation. And just the last bit on this page and the last bit in this part of the video, and we're going to look at the difference between a base and an alkali. So a base by definition is a metal oxide or metal hydroxide, which neutralizes an acid to produce a salt and water. So it's basically a substance that's going to react with an acid to form a salt and water only, and by definition that's neutralization. And what an alkali is a soluble base. So we could replace our definition of an alkali with a metal oxide or hydroxide, which neutralizes an acid to produce a salt and water that is soluble in water. So our alkalis must be soluble. And what you can do is look at the back of your periodic table to work out the solubility of a compound. So have a look at the back of your periodic table now, and you can see there are some solubility rules. So we can see here, I've put together a diagram that hopefully helps you there. All alkalis are bases, but not all bases are alkalis. And that sounds a wee bit confusing, but let me say it again. All alkalis are bases, but not all bases are alkalis, and you can see that from our diagram. So essentially our alkalis are a special type of base in that they're soluble. So these here, they are all soluble. The things on the outside of the alkali circle, so I'll write soluble here. The things on the outside of the alkali circle, so that are just in the base, I'll highlight them a different colour. Mine's quite messy, but you can make yours a bit neater. These are all insoluble. They do not dissolve in water, but they still will react with an acid to neutralise it. But alkalis are just soluble bases. That's the only difference. That's us at the end of part 1 of this topic. So when you're ready, you can move on to part 2.